Welcome back to Think Cosmos, where we ponder the universe's deepest secrets and wonders. Water is often touted as the key ingredient for life as we know it, the universal solvent that makes Earth so special. So whenever astronomers study young stars and new planetary systems forming, a burning question has been, is water there too, right from the start? We know our own solar system story. Comets and icy asteroids delivered water to the early Earth, but that water originally condensed out in the frigid outer regions of the Sun's protoplanetary disk. Until now, we had circumstantial evidence that other forming systems also have water ice, but nothing definitive. That's why a recent discovery is so exciting. For the first time, scientists have clearly detected frozen water, actual ice, in the dusty disk around a young star very much like our Sun, only much younger. It's a bit like a cosmic eureka moment. We expected it, we hoped for it, but now we can finally say we've seen it. And it's all thanks to the incredible capabilities of the James Webb Space Telescope. JWST. Webb turned its gaze to a star called HD 181-1327, which is about 155 light-years away, a neighbor in cosmic terms. This star is interesting because it's fairly similar to the Sun in mass, but it's just 23 million years old, a baby compared to our 4.6 billion-year-old Sun. Importantly, it's surrounded by what's known as a debris disk. Think of a debris disk like a kind of second-generation disk around a star. The primordial gas has gone away, and what's left is dust and rubble from colliding comets, asteroids, and perhaps the leftovers of planet formation. Our own solar system has debris disks. The Kuiper Belt and even the zodiacal dust could be considered analogous, but this star's disk is younger and likely denser with debris. Earlier, NASA's Spitzer Space Telescope, Webb's infrared predecessor, had picked up hints in 2008 that there might be something like ice in this disk. But Spitzer didn't have the resolution or sensitivity to nail it. JWST, with its powerful infrared spectrometers, can not only detect the presence of certain materials, but confirm their composition via spectral fingerprints. And boy, did it deliver. Webb's observations unambiguously showed the signature of crystalline water ice spread throughout HD 181-1327's disk. Let's unpack that. Crystalline water ice means it's water in solid form. Ice show ice with an ordered crystal structure, similar to the ice cubes in your freezer, albeit probably in tiny grain form mixed with dust. The fact that it's crystalline also tells us something about its history. Crystalline ice in space often forms when water vapor refreezes slowly, or when ice gets heated and annealed a bit. In comets in our solar system, we find both amorphous and crystalline ice, and that can indicate whether the ice has ever been warmed above a certain temperature. Above a certain temperature. The presence of crystalline ice in this disk could hint that some processing, like mild heating by the star's light, has occurred. The scientists describe the ice grains as being like itsy-bitsy, dirty snowballs distributed throughout the disk. That's a cute way to put it. Essentially, these are ice particles mixed with dust, hence dirty. This immediately evokes the image of comets, because comets are often called dirty snowballs. They're mixtures of ice and dust and rock. And indeed, what Webb saw in this disk is very analogous to comets in our solar system. In fact, one of the astronomers pointed out that the spectra Webb obtained from this star's disk looks surprisingly similar to the spectra Webb recently took of objects in our own Kuiper Belt, the realm of icy bodies beyond Neptune. It's as if HD 180-1327's disk is a young version of the Kuiper Belt, chock full of icy grains and probably larger icy bodies forming or already formed. One striking result was that the ice isn't evenly spread. Webb could tell that most of the water ice was concentrated in the outer parts of the disk, far from the star, where it's cold. Near the star, they detected almost no ice, which makes sense because closer in, the temperature rises and any ice would sublimate, turn to vapor, if it gets too warm. This mirrors our solar system. Within the snow line, around the orbit of Jupiter in the early solar nebula, water couldn't exist as ice, only as vapor. Beyond that line, it was cold enough for ice to condense. That's where Jupiter's icy moons and Saturn's rings and all the comets come from. So Helio 180, 1327 has a sort of snow line as well. Interior region drear, outer region frosty. They even suggested that perhaps the inner region's ice grains either got vaporized or locked up into planetesimals, basically forming the cores of future planets or large asteroids that JWST can't detect because they're solid bodies, not loose dust. It could be that in the inner disk some big rocks have already gobbled up the ice, or the star's ultraviolet radiation has cleared it out. This discovery is a big deal for a few reasons. Firstly, it confirms that the ingredients for making water-rich worlds are present early on around other stars. This disk is only at 23 million years old, meaning planets might be still forming or recently formed there. If water ice is around, it can be incorporated into comets and protoplanets, which means down the line. If there's a rocky planet in the habitable zone, comets could crash into it and deliver water, just like they did on Earth. In other words, the potential for creating Earth-like, ocean-bearing planets elsewhere just got a stronger observational foundation. And secondly, it gives us direct insight into the planet formation process. Water ice isn't just important for habitability. It also plays a role in how planets form. In the cold outer disk, ice helps dust grains stick together. Imagine wet snow versus dry snow. Wet snow packs into snowballs much easier, so ice can accelerate the growth of planetesimals. Also, ice adds mass. A lot of the outer planets in our solar system have a lot of ice in them, like the cores of Jupiter and Saturn might have substantial ice. Uranus and Neptune are called ice giants for a reason. So saying ice in that disk means it's at the right place to build gas giants and ice giants. Perhaps HD 180, 1327 will have its own versions of Jupiter or Neptune in the making. Another fascinating aspect. This water ice detection was not a one-off lucky break. It's likely the first of many. Webb is just getting started on exploring planet-forming environments. The fact that it could confirm crystalline water ice in one debris disk means we can now go survey others. We might soon find out how common this scenario is. Is every debris disk loaded with water ice? Do only some have it? And do the amounts vary? We could even compare younger protoplanetary disks with gas still in them to older debris disks to see how water transitions from vapor to ice to being locked in planets. One of the researchers nostalgically mentioned that 25 years ago, as a grad student, they suspected ice should be in these disks, but we just didn't have the tech to see it. Now, with Webb's superior sensitivity and spectroscopic power, it's finally visible. They described seeing the data and noticing how it resembled what we see in our solar system's outer reaches. That's a huge validation that the basic chemical makeup of planetary systems might be quite universal. Now, let's think broadly. Water ice in a debris disk today means a lot of it is likely residing on or in comet-like bodies. In our solar system, the Kuiper Belt objects and comets are time capsules of the early solar system's water. HD 181 1327 is effectively showing us the equivalent in another system. It's like confirming that comet nurseries exist around other stars too. And these comets, if they get perturbed and sent inward, maybe by a giant planet's gravity, could rain down on inner rocky worlds, delivering oceans. We might be witnessing a phase analogous to what happened in our own system about 4 billion years ago. The so-called late heavy bombardment, where swarms of comets and asteroids slammed into the inner planets, possibly delivering water to Earth. AD 180-1327 might experience something like that in the future, or maybe it's ongoing. If its disk is disturbed by planet migration. Importantly, they specifically mention crystalline ice, similar to Saturn's rings and Kuiper belt objects. Saturn's rings are thought to consist largely of water ice, which is relatively pristine. And you can see the clarity of those ice chunks in the ring's brightness. The Kuiper belt has many bodies with crystalline ice surfaces as well, indicating they have been either heated slightly or have undergone some processing. In interstellar space, ice that forms on cold grains is usually amorphous, disordered. So crystalline ice in a disk implies that maybe ice formed closer to the star, where it was warmer and got crystallized, then was transported outward. Or it could mean that shocks in the disk annealed the ice. Either way, it points to dynamic processes in the disk. Another neat angle. By confirming water in these disks, Webb opens the door to studying the chemistry of other crucial compounds in planet formation too, like carbon dioxide ice, methane ice, ammonia ice. Ammonia ice? In the findings, they noted that other frozen molecules exist in space, like corn ice, which Webb can also detect under the right conditions. With water confirmed, we'll likely hunt for these others. That will build a more complete picture of the volatile inventory. Volatiles are substances like water, cool, etc., which are gaseous at higher temperatures, but freeze in cold space in new planetary systems. From a narrative standpoint, there's something almost poetic here. We've captured a glimpse of other solar systems making their own oceans. Not literally liquid water oceans yet, but the raw material, the ice that could melt on a future planet to form oceans. It's like seeing the cosmic kitchen, stocked with the essential ingredients for life soup. And it raises that tantalizing question. If many sun-like stars start out with water-rich disks, then many Earth-like planets might start out with access to water. Does that up the odds that life could arise elsewhere? It certainly doesn't hurt the case. Water availability was a critical factor for life here. Knowing it's likely common around other stars' planets as well is encouraging for the search for extraterrestrial life. This discovery also helps refine our understanding of debris disks versus protoplanetary disks. Percy 1030-1337. Disk is considered a debris disk. The star is beyond the age where a lot of primordial gas remains. We used to think debris disks were mostly just dust from collisions, relatively dry. But clearly, this debris disk has a lot of ice in it, which suggests those collisions involve icy bodies, and that there's still a lot of frozen content there. The line between a gas-rich young disk and a debris disk might be blurrier than thought, at least when it comes to ice content. One more interesting detail. They mention all the frozen water is paired with fine dust grains. So the ice might actually be coating dust grains. Literally, icy dust. In space, water can condense on dust motes, forming ice mantles. So some dust grains in this disk are like tiny snowballs themselves. Over time, these icy grains can stick together more easily than dry grains. Ice is sticky, so the presence of ice could mean that this disk's dust is clumping effectively into larger aggregates. The first steps of planetesimal formation. It's like having glue, ice, on the dust that makes planet formation easier. It underscores water's dual role. Future oceans and current planet-making glue. The results were published in Nature, which means they were significant and robust. And the way NASA presented it as another first in a press release shows they consider it a landmark JWST finding. So, stepping back, what's the big story to tell? It's that we have direct evidence of water, as ice present in the formative stages of a planetary system. This is a milestone in our journey to understand the origins of potentially habitable worlds. For a narrative, you could imagine a narrator starting by painting a picture of how vital water is, then explaining how we suspected it's common in planet formation but lacked proof, and then Webb giving us that confirmation. It's a triumphant moment, akin to finding a missing puzzle piece in the story of how to build a planet. We can also make it engaging by saying something like, picture a ring of icy dust around a young star, a glittering belt of comets and frost. That's what Webb saw, a scene that could eventually lead to alien oceans, and tie it to our own cosmic heritage. We've long wondered if other newborn planets get the same life-giving water that Earth did. And now we see that Mother Nature indeed provides the coolant and the cocktail for other worlds too. Finally, wrap up with a reflective or forward-looking question. Maybe about how common life might be if water is so readily available, or something about what other ingredients Webb might find next. If you could rewind time and watch our own solar system form, you'd see a swirling disk of gas and dust around the newborn sun. And hidden in that disk, countless grains of water ice beginning to clump together. Those ice grains would eventually help build comets, icy moons, and even deliver oceans to Earth. For decades, scientists have suspected that this recipe, water included, isn't unique to us. But seeing it elsewhere, directly, has been beyond our reach. Now, at last, the James Webb Space Telescope has given us a vivid confirmation. It has detected frozen water in the dusty disk around a young star, offering a snapshot of another solar system's pantry, stocked with the ingredients for planets and maybe life. Let's set the scene. The star in question, named HD 1811327, is a young sun-like star about 155 light-years away. Imagine a star similar to our sun, but in its toddler years. It's only about 23 million years old. Around this star is a broad debris disk. Think of it as a sprawling ring of cosmic leftovers, filled with dust and chunks of rock and ice, probably the detritus of early planet formation and ongoing collisions. Picture something akin to our Kuiper belt, or a giant ring of comets, or a giant ring of comet. This is the kind of environment where planets either have recently formed or are in the making, and where smaller bodies like asteroids and comets are plentiful. Astronomers pointed the ultra-sensitive eyes of JWST toward this system and used its spectroscopic instruments to essentially fingerprint the materials in that disk. What they found sent a ripple of excitement through the community, a clear signature of crystalline water ice coating the dust and floating in that disk. Ice. In plain terms, Webb saw icy dust grains, tiny, dirty snowballs, everywhere throughout the outer reaches of that system. For the first time, we have definitive evidence that a young sun-like star's disk has as much water ice as we expected, confirming that other nascent planetary systems have water ready and available. Why crystalline ice? In space, not all ice is the same. Crystalline means the water molecules are arranged in an ordered lattice, as opposed to amorphous ice, which is more jumbled. Here on Earth, pretty much all the ice we encounter, in ice cubes, snowflakes, etc., is crystalline. In space, ice can form as amorphous at extremely low temperatures, but if it gets mildly heated or forms slowly, it becomes crystalline. Webb's detection specifically showed the ice has the crystalline structure. Interestingly, the same kind found in places like Saturn's rings, or the icy Kuiper belt objects in our own solar system. In fact, one astronomer remarked that the Webb data from this stars disk looked strikingly similar to observations Webb recently made of objects in our Kuiper belt. It's as if nature is rhyming. A young star's icy disk out there, and our familiar icy regions here in the solar system, share the same kind of water ice. The distribution of that ice was telling too. Well, Webb's observations indicated that the majority of the water ice lies in the colder outer parts of the disk, far from the central star, which is exactly what you'd expect. Close to the star, within a certain radius, it's too warm for ice to survive. Any water would be vapor. Farther out, beyond the stars, snow line, temperatures drop and water freezes solid onto dust grains or as frost on larger particles. That's precisely what Webb saw, a kind of cosmic frost line. When they looked nearer to the star, they found much less ice, likely because any ice there either sublimated, turned to gas, due to the star's heat, or got locked up in developing planets or big asteroids. This inner region might have water in vapor form that Webb could detect in other ways. But the ice itself is mostly in the disk's outskirts. Now, why does this matter so much, aside from being a cool, pun intended, detection? For one, water ice plays a crucial role in building planets. In those outer disk regions, ice-coated dust grains stick together more readily than dry dust would. But imagine making a snowball. It's a lot easier when the snow is a bit wet and packs together. Similarly, icy grains glom onto each other, forming pebbles, then rocks, then comets or planetary cores. Water ice essentially acts as the glue and also adds a lot of solid material mass to nascent planets. It's thought that the cores of Jupiter and Saturn formed with a significant help from accumulating ices. And for Earth-like planets, we believe that water was delivered by icy bodies, comets, water-rich asteroids, from outer regions. So saying a reservoir of ice in HD 181,013.27. Disk suggests that if there are rocky planets in the inner part of that system, or will be in the future, they probably have a mechanism to receive water via comets spiraling inward or giant impacts bringing ice-rich material to them. This detection also opens a new chapter in comparing planetary systems. We've found thousands of exoplanets by now, but we're only just starting to directly study the disks where those planets originate. Now that Webb has shown it can pinpoint something as specific as water ice, we can survey other stars' disks. Is HD 181,013.27 special, or do most young sun-like stars have ice-rich disks? Perhaps some disks might even have signs of other ices, like carbon dioxide ice or methane ice. Webb's instruments can detect those too, if they're abundant. In HD 181,013.27's case, water ice was the standout feature, which makes sense because water is usually the most common condensable substance in protoplanetary disks, after hydrogen and helium, which don't form ice at those temperatures. Another exciting implication: it's a huge boon for the idea of widespread habitability. We always talk about exoplanets in habitable zones, the region around a star where liquid water could exist on a planet's surface, but that assumes the planet has water to begin with. If many forming planetary systems are as water-loaded as this one, then a lot of planets out there are going to start off with the potential to have oceans, or at least significant water content. It nudges the odds toward the optimistic side in the air we alone wager. After all, Earth needed its water delivered to become the blue marble of life. Seeing that other systems have the delivery trucks, comets, ready to go is encouraging. One particularly heartwarming aspect of this discovery is how long scientists have been waiting for it. A researcher on the team recalled how, a quarter-century ago, they theorized that debris disks should have ice but simply couldn't observe it. The technology just wasn't there. Telescopes weren't quite powerful or sensitive enough to distinguish the spectral fingerprints of water ice in a faint, distant disk. Now, with JWST's cutting-edge infrared capabilities, the evidence practically jumped out of the data. It's a testament to human curiosity and perseverance. An idea seeded in the 1990s finds confirmation in 2025, thanks to a telescope that orbits 1 million miles from Earth and can sniff out the composition of dust around another star. To give you a sense of how Webb identified the ice, it used a technique similar to how a prism splits light into a rainbow, but in the infrared. In that rainbow of the star's disk, water ice has characteristic absorption features, essentially dips at certain wavelengths where the ice absorbs light. Webb saw those dips clearly, and they matched the laboratory measurements and known spectra of water ice. There's essentially no other common substance that could cause exactly that pattern in the data. So it was a clear shout of, "Hey, there's water ice here," from the disk. Furthermore, the presence of fine dust alongside the ice was inferred because the spectrum shows traits of small particles, as opposed to, say, huge solid ice chunks. This intimate mixing of dust and ice, basically icy dust grains, that tells us we are looking at a very young, active environment where everything is still in bits and pieces, not yet fully formed planets. Analogy. Imagine looking at cookie dough before it's baked. You see the sugar, the flour specks, maybe some chocolate chips. Webb essentially saw the sugar and flour of a future planetary system. The raw stuff that, given time and proper conditions, will bake into planets, moons, asteroids. And one of the key ingredients is indeed water, ice. No surprise for a good recipe for life. The results from HD 181,013-27 serve as a beautiful cosmic mirror, reflecting our own solar system's past. It's like we have a time machine not for our system, but to see a similar system in its youth. Our sun at 23 million years old likely also had a debris disk teeming with ice and dust. Earth wasn't around yet. Earth formed a bit later, or was in the very early stages around that time. But the building blocks of Earth, including water, were present in the sun's disk. Now we have confirmation the same scenario is unfolding elsewhere. This discovery also underscores how common processes in the universe can be. The star in question isn't particularly rare or weird. It's one of many sun-like stars out there. If this one has water ice in its disk, chances are a lot of its siblings do too. And so far, everything we've been learning with exoplanets and disks suggests a rich diversity of outcomes. Some stars form Jupiter-like giants, some only small rocky worlds, etc. But the fundamental ingredients in physics seem to be universal. Hydrogen, helium, water, carbon compounds. They're everywhere. The cosmic kitchen is well stocked in general. So, stepping back and thinking big picture, we now know water is present in the formative stages of other planetary systems, not just as vapor, but as solid ice ready to be delivered. This answers a long-standing question, and naturally leads to the next. We'll want to know how much water is out there in different systems. Is this disk unusually water-rich or water-poor compared to others? Are there systems where maybe water ice is scant, implying maybe they won't have many comets, or they formed in a different way? Webb will be instrumental in answering those questions too. And of course, whenever we talk about water in space, the question of life is lurking in the background. Water alone doesn't guarantee life. You need the right conditions and other chemistry. But it's a big piece of the puzzle. It feels a bit like we're assembling clues for a future where we might find evidence of life beyond Earth. Think of it this way. If someday we detect an Earth-like exoplanet in the habitable zone, and even see signatures in its atmosphere that hint at possible life, like oxygen, or maybe some weird chemical imbalance that screams biology, we will also look back at that star's history, knowing that, yes, The star had a water-rich disk and likely delivered oceans to that planet. Will make the case for life there even more compelling. There's also a romantic aspect to this discovery. Water is a common thread that connects us to the cosmos. The water in your glass right now is ancient. Some of it was forged in space and delivered by comets eons ago. Now we see other worlds might be going through the same delivery process. And it's almost poetic to think that distant future aliens on a planet around HD 181,327 might one day drink water that we witnessed as ice in their system long before their planet even fully formed. In a way, Webb allowed us to witness a step in the cosmic life cycle of water. From ice grains in a disk to, potentially, rivers and oceans on planets yet unborn. As the grand finale, let's marvel at what this means in the context of our ever-evolving understanding of the universe. We often look for firsts in astronomy. The first exoplanet image, the first black hole photo, etc. This was a different kind of first. The first direct confirmation of water ice in an exoplanetary debris disk. It's one more piece of evidence that the story of how planets and life come to be is likely a universal story, replayed across the galaxy with different characters and settings but similar plot points. And it prompts a profound question. If water, the essential catalyst for life, is so abundant in young planetary systems, could life itself be far more common than we ever dared to dream? That thought sends shivers down the spine. In a good way. We're learning that the cosmos sets a pretty hospitable stage, at least chemically speaking. The rest might just be a matter of time, chance, and evolution. So next time you sip some water, consider this. The galaxy is brimming with water too, hidden in the cold embrace of dusty disks around countless stars. With each new discovery, we're finding that the conditions that birthed life on Earth may not be rare at all, but part of a grand cosmic tapestry. Isn't it wondrous to think that the same water that cradles life here is being woven into new worlds light years away? And if water is everywhere, waiting in those cosmic wings, what extraordinary possibilities might be waiting to flow forth on planets we've yet to discover?